Welcome to the Costa Aquatechnic CPD injectable systems for cracks, joints, voids and curtain waterproofing. The contents of this training are split into 7 sections as follows. A short introduction to Costa Aquatechnic and to myself. What can we do with injection resins? Key types of products available. We'll cover polyurethane resins, epoxies, acrylic gels and microgrouts. Ancillary products. We'll look at injection packers, injection pumps, cleaners and special mortars. And health and safety. And detailed application guidance. We'll go over the main injection techniques in more detail and have included some interesting case studies. Learning objectives. By the end of this CPD, you'll have increased your knowledge on the different uses of injectable products. You'll be able to understand the strengths and weaknesses of the various systems and in what situations they will be relevant. And you will have a solid introduction into the injection techniques used and the types of equipment needed. But firstly, I would like to introduce myself and Costa Aquatechnic. My name is Alex Lynn. I'm the Technical Director for Costa Aquatechnic. I've been with the company for several years and I'm a CSSW qualified surveyor and designer. Costa Balcony is located in Aurich in the northwest of Germany and was founded by Johann Costa in 1982 as a manufacturer of waterproofing systems. Today, Costa Balcony is a group of 26 companies with worldwide activities. Costa specialises in the development and production of waterproofing systems and construction chemicals. Our UK operation was established in 1999 to provide distribution and local technical support for the Costa range. We provide a free, in-depth technical consultancy service, helping you to find the best solution for each individual project. For remedial works, we can help to ensure that a correct diagnosis is made, which is the first step to finding a cost-effective and permanent solution. For new builds, we can provide individual detailed drawings prepared by our CSSW qualified staff to suit even the most complex of structures. Costa offers a comprehensive range of materials. Our high quality and long-lasting systems sustainably increase the life cycle of buildings by avoiding moisture damage, less repair work is necessary, and energy consumption is reduced because insulation values remain intact. Costa offers products and expertise in the following areas. Waterproofing of below-ground structures such as basements, either externally or internally. Long-lasting and sustainable single-ply roofing membranes with Costa TPO. Leak stopping with a full range of injection resins, gels and water plugs. Wet room systems, including tanking, made-to-measure shower tray formers and bespoke factory-produced full-floor solutions. Chemical DPCs with unique properties that work in even the most difficult situations. Jointing systems based on sealants, elastic tapes, compressible materials and hydrophilic profiles. Concrete protection and repair systems and fully bonded vapour barriers for sealing concrete slabs prior to the application of resin or vinyl floor finishes and screeds. Costa products are manufactured according to German and European quality standards. In-house quality control and research and development give us full control of the technical properties of our products. Close communication with our customers leads to new ideas for new solutions and eventually to new products. Costa production is certified according to ISO 9001 and our products are frequently tested by independent institutes and carry CE or UKCA marking where appropriate standards exist. We are committed to preserving and protecting the environment. Our products are solvent-free are formulated to protect nature as well as the health of the people who live and work with them. Our environmental policy is clearly communicated to all employees and states our intent to reduce our carbon footprint, improve recycling, reduce reliance on packaging, minimise waste, and improve the efficient use of natural resources. So, let's get started by looking at what we can achieve with injection systems. First up, injection of leaking cracks or construction joints. This sort of work would normally be carried out with foaming polyurethane resins. Cracks can occur due to shrinkage, movement, or stress. With injection resins, we can stop the leaks and elastically seal the crack pathway. Another area that often causes problems is the wall-to-floor junction. It may be that the concrete wasn't properly vibrated, or there was a problem with the water bar, or perhaps the shutter wasn't tight, letting some of the cement paste leak out and creating voids. With injection resins, we can seal this joint either with a borehole injection or by pumping resin into a pre-installed injectable water bar. Resin injection isn't just about stopping leaks. In some cases, resin injection is used to restore the structural strength of the concrete. For instance, when you have cracks in a load-bearing concrete beam or cable anchor blocks, with the latest generation of epoxy resins, even the smallest cracks can be injected, restoring the original strength of the concrete. At this point, it is interesting to ask the question, what is a crack? Would anyone like to answer this question? We'll have a think about it. There are many correct answers, but an answer will be provided later on in this presentation. When movement joints leak, they can be very difficult to repair. However, with a polymer-modified acrylic gel, these joints can be sealed elastically, even when wet. It is always preferential to waterproof below-ground structures from the outside, positive side. However, with existing buildings, it is often impossible to excavate the basement. You could waterproof internally with a cementitious coating or a cavity drainage system, but if it's historic brickwork or stonework, the only option is to waterproof externally, but from the inside. This is called curtain injection and is normally undertaken using acrylic gels. Void filling. This is a good solution where a non-maintainable cavity has mistakenly been created below ground. Other voids encountered are those formed during the concrete pour due to lack of vibration, bad rebar placement, or leaking shuttering. For these voids, within the structural concrete, a microgrout would normally be used. So, having looked at what we can do with injection, we can now look at the types of injectable products available. The first category is polyurethane resin. There are three main types of injectable PU resins. 2 iron 1 resins. These foam on contact with water, or without water, they form an elastic solid body resin. 2-component highly elastic solid body resins, and 1-component fast foaming water stopping resins, either with or without an accelerator. We will look at each of these in a little more detail in the coming slides. There is another category which we won't be covering, and that is slab jacking resins. This is where they inject a very fast reacting foam with strong expansion beneath a concrete slab to lift or realign it. This is a highly specialist and potentially hazardous activity, which we are not involved in. All modern PU resins are based on MDI isocyanates and are free from the more harmful TDI isocyanates, which unfortunately can still be found in the UK market. You can normally spot these as they have a skull and crossbones on the label. 2-in-1 resins are very versatile. They are a 2-component polyurethane, but work in a very interesting way. As soon as you mix the part A and B together, the reaction has already started. If you just left that mixture on its own, it would cure to form an elastic solid body resin, as shown on the right. This would be ideal for injecting into dry cracks to achieve a permanently elastic seal. However, if you introduce the freshly mixed material to water or dampness, it will react to make a foaming polyurethane. This one material can be injected into dry, damp, or wet cracks. When you inject into a wet crack, the material reacts to form an expanding foam. This uses up some of the water in the crack and pushes the rest of the water out. The foam is fully formed in about 6 to 10 minutes. It is then re-injected with the same material after 15 to 20 minutes. The new injection will push back the soft foam and fill the crack with a solid body of resin. There is no water contact during the second process, therefore the product does not foam. The elastic solid body resin has much greater elasticity than the foam and will create a permanent seal. Next, we have 2-component highly elastic solid body resins. These are not designed for active leak stopping, so you shouldn't be used for water-filled or actively leaking cracks. These materials are very thin, so good for fine cracks or small channels. They have a long pot life of about 4 hours, so are ideal for injecting long distances from a single packer. These types of resins are also used for hose injection. If an injection hose has been cast in during construction, then you can go back later and pump in resin to create an elastic seal. Single component elastic foam. This is a fast-acting polyurethane resin. It reacts directly with water to form an elastic foam. If you injected it into a dry joint, nothing would happen. It must have water to react. The normal reaction time is about 30 to 60 seconds, but with an accelerator, this can be sped up to within about 20 seconds of water contact. The type of resin is mainly used for fast leaking areas where a slower resin could get washed out. With this type of resin, a system can be designed to stop even the heaviest of water ingress. It's not just about the resin itself though, but also the specialist injection techniques that we will investigate later. It is very important when selecting a single component resin that you choose one that produces an elastic foam. There are some rigid single component foams in the market. These can stop water leaks, but will shrink back over time or crack if there is any movement. An elastic foam will grip firmly to the internal surfaces of the crack and will allow for continued movement. Next, we're going to focus on acrylic gels. But firstly, what is a gel? Acrylic gels are different technology to the polyurethanes. They are made of metacrylics. They behave in a different way to polyurethanes and present several advantages. Acrylics do not react with water, but form chains of polymers that are connected so strongly that they bind water inside their structure. Since acrylic gels contain water, they are in a state between solid and liquid, giving it a viscoelastic consistency. They are highly elastic, but if physically split, they tear in a similar way to edible jelly. The connections between the polymers are so strong that they can resist a water pressure of over 7 bar. Most acrylic gels fit into one of 3 categories: fixed ratio gels, variable injection gels, and polymer modified gels. We will start with the fixed ratio gels, as these are the default product for curtain injection. They are supplied in 3 parts: A1, A2, and a B, which is a salt. You pour the A2 into the A1 drum and mix by simply rocking from side to side. The part B is emptied into the second drum, which is then filled with clean water to the same volume as the first drum. The pre-mixed A and B components are then pumped separately through an acrylic gel pump at a ratio of 1:1. The materials only come together at the mix head just before entering the injection packer. There is a third hose in the pump, which is for water and is used for flushing and cleaning the mix head. The gel can also be stirred by hand and poured, but you should only mix what can be used within a few minutes. This type of gel is environmentally friendly and will not pollute the watercourse. With the latest gels of this type, all the salt is used up in the reaction so they don't cause corrosion to any metals within the structure. When first mixed, the material has an extremely low viscosity of 4 millipascals. As a comparison, water would be 1, sunflower oil is approximately 48, and runny honey would be at least 2000. So the gels seem pretty like water. After 3 to 4 minutes, the material will enter the cloud phase, where the material starts to show a purple tinge, then slowly turns white. By 6 to 8 minutes, the network phase, the material begins to rapidly start to thicken. After about 15 minutes, the reaction is complete. The great thing about fixed ratio gels is that there's no weighing or measuring to do on site. Everything is set to the perfect ratio for most applications. Here we can see a demonstration of an acrylic gel in action. In the small container we have sand. In the right-hand beaker we have the part A, which consists of the part A1 and A2. And in the other beaker we have the part B, which consists of the B1, which is a special salt, mixed with water. You can see that the two parts take up the same volume. After mixing the part A and B together, some of the mixture is poured into the sand and some is left in the beaker. Note that the material isn't stirred into the sand but penetrates easily, just as water would. After about 3 minutes, the material starts to go cloudy, and in about 6 to 7 minutes, it forms a gel, which gets gradually harder over the next few minutes until the reaction is complete in about 15 minutes. At this time, the gel is very solid and has a firm, rubbery texture. The sand has completely consolidated by the gel and is now a firm, waterproof mass. The variable reaction gel has most of the same properties as the fixed ratio gel, but has a higher degree of versatility. Whereas the initial gel time for the fixed ratio gels is about 8 minutes, the variable reaction version can be customized to gel when you need it to. The gel time can be set to anywhere between about 10 seconds and 2.5 minutes. The time is altered by changing the dosing of the B component between 50 grams and 1 kilogram. The material is mainly used for situations where you have very heavy flows of water. A polymer modified gel is the same as a variable ratio gel, but uses a special polymer combined with salt for the part B, instead of water and salt. This has 3 beneficial effects. It makes the reaction time faster, it improves the flank adhesion in joints, and it increases the resistance of the gel to drying out when there is no contact with ground moisture. This gel is mainly used for refurbishment of failed expansion joints. It can be used with minimal surface preparation on wet joints and has incredible elasticity and adhesion. Now we come to epoxies for structural repair. It is always important to choose one with low viscosity, particularly when injecting fine cracks and networking of cracks. These products are used for structural repair by either pressure injection, pouring, or vacuum injection. The best products have a very low viscosity of 175 millipascals. This is less than half the viscosity of some of the older style epoxies used for injection and will be described as a thin liquid. The low viscosity means it can be used in even the smallest of cracks at very low injection pressure and can even be gravity fed into repaired floor cracks. This type of low viscosity epoxy also has very good adhesion even to damp concrete and cures to a strength of 80 newtons per millimetre squared, so can fully restore the structural integrity of the concrete. Now for something completely different. Microgrouts aren't injection resins, but cementitious injection materials. They are used for filling large voids in concrete and for restoring the structural strength. They are thicker than epoxy resins, but still very thin for a mortar, with very good flowability. The maximum particle size is 0.1 millimeters. In theory, you could fill cracks down to 0.2 millimeters. However, when dealing with any cracks under 2 millimeters, we would always recommend an epoxy resin. You can do crack injection with a microgrout, but there are better products available. Where microgrouts really come into their own is for filling large voids within concrete. With microgrouts, we can fill voids with a product of a similar strength and characteristics of the concrete surrounding it. The material is supplied in powder form and is simply mixed with water. It's pumped using a peristaltic pump or any other grouting pump. The final compressive strength after 28 days is 60 newtons per millimetre squared. That's all the injectable products. But what ancillary products do we need to facilitate the injection? Firstly, injection packers or lances. These are the mouthpieces through which the injection product is delivered into the crack or void. They come in all different shapes and sizes. Impact packers are generally made of plastic with fins or lamellas along their sides. The packer is force-fitted into the borehole with a hammer or drive-in tool. As it goes in, the lamellas are forced out of shape and make a negative seal against the walls of the borehole, locking the packer into position. Some drive-in packers have a non-return valve, some have no valve at all, and some have an optional valve piece. They can be pushed on if required. Impact packers are normally left in the wall. After injection, you can cut off the protruding piece and drive the rest deeper into the wall. Some are designed to snap off at a particular point within the hole if hit with a hammer. This makes the removal process very quick and easy. The most common type of injection packer is the expanding packer. These are made from metal, they have a screw thread, and when you tighten the shaft, the rubber piece in the hole becomes compressed lengthways, forcing it to expand outwards, firmly gripping the walls of the borehole. These packers either have a grease nipple or panhead fitting to connect to the injection hose and pump. These connection pieces contain a ball valve, which ensures the injected material won't leak back out when you stop injecting. The one-day packer is designed for small injection jobs, where the contractor wants to get in and out in one day. It is similar in principle to the standard packers, but has an additional non-return valve at the end that goes into the wall, as well as a locking ring halfway up the shaft. When you are finished injecting, you can unscrew the shaft, leaving the rubber part tightly in the borehole. The injection resin can't flow back out due to the extra valve, so you can fill the mouth of the borehole straight away. With a normal packer, you would have to wait for the injection material to cure before unscrewing it. There are special gel packers specifically designed for curtain injection. The packer comes in 3 pieces: a connection piece, a shaft which is cut to suit the wall thickness, and a special mouthpiece to push the material out sideways. During the injection process, we often use fast-setting mortars and water stops. The most common use is for sealing the front of the crack prior to injecting. In the case of a dry or damp crack, this can be done with a fast-setting, high-strength mortar with a set time of about 5 minutes. Why do we seal the front of the crack if it's dry though? To keep the injection resin in the wall during injection. Because when you start injecting, the resin's under pressure. To equalise that pressure, the resin looks for the fastest and easiest route out. This will often be straight out the front of the crack and down the surface of the wall. But we want the resin to move slowly along the crack pathway and seal the whole depth of that crack. Therefore, we use the mortar to seal off this escape route. The same mortar is then also used after removal of the injection packers to seal up those boreholes. In the case of flowing water, we may need to use a cementitious water stop to temporarily stop the leakage, slow the leakage, or push the leakage to a particular point. Water stops set in about 2 minutes and slightly expand, so creates a very tight seal. Different injection products require different types of injection pump. These vary from a simple hand pump, which is basically a grease gun, to a pneumatic gel pump with 3 pistons. The choice comes down to what you are injecting and how large the project is. The last of our ancillary products is cleaner. Proper cleaning is of the utmost importance. If the injection material is allowed to set in the pump, then you will be incurring expensive repair charges. PU resins are always cleaned with a PUR cleaner. This is solvent-free but very good at shifting fresh resin. For the gel pump, it's a little easier as the A and B components are not mixed together until they reach the mix head. The material is a lot thinner and less sticky than polyurethane resins. So for gel pumps, we can just clean with water. For microgrouts, you can again use water to flush out the pumps. You should also use foam cleaning balls to help clean any mortar residue from the delivery hose. The health and safety and well-being of the people that work with waterproofing materials must be considered and stringent policies put into place. All UK construction sites require operatives to wear basic PPE, but when working with specialist materials, there may be additional requirements such as ear defenders, dust masks or face shields, gloves, overalls, and forced ventilation. None of the Costa injection materials contain solvents, but eye protection and gloves should always be worn. Cured material, particularly epoxy or PU resins, are very difficult to remove from your skin. For some injection materials, forced ventilation or even breathing apparatus could be required if in confined areas. We also have to be careful in working with drills, particularly working in areas where the structure is compromised. The main contractor should prepare a cost risk assessment for every site where crack injection works are being carried out. The material and application risks are made clear on the manufacturer's MSDS sheets. We will now look a little more into the specification and application of injection products. Before specifying a particular system, we try to understand the following. So, the cause. By understanding the cause of a crack, we better know how to fix it. If it's a shrinkage or settlement crack, it may well have finished its movement phase and a rigid injection solution may be appropriate. If it's due to changing temperatures or moisture conditions, it may move on a cyclical basis and would require a flexible solution. If it's caused by intermittent overloading, then it may be that further structural measures are required to prevent occurrence. Monitoring. If the crack is still moving, how do we know? In some cases, it is agreed to monitor a crack over a period of time. In this case, a monitoring gauge is used. The simplest form is a gypsum mark, as shown in the picture. This will show movement by cracking across the narrow centre section. A more complex type of gauge is made up of two parts which are firmly bonded on each side of the crack. A scale will show whether the crack is moving, and readings can be taken at regular intervals. The course. If we can learn the course of the crack, we often see that it interacts with other elements such as day joints or expansion joints. This may be the way in which water is being fed into that defect. Understanding the interaction of the crack within the structure can help us select the best location for the injection packers. The width of the crack. This will affect the amount of injection material used, the type of injection material, and the spacing between packers. Previous attempts. If someone has made previous attempts to seal a leaking crack, the connectivity between the boreholes can be affected. The crack is partially filled with old resin, which may have shrunk back slightly. It is therefore very difficult to find a way of hitting all the weak spots. It may be that you need to drill additional boreholes and allow for repeat visits to ensure sealing of all the leaking areas. This is a crack survey that was carried out on a wind turbine base. Producing such a survey takes a lot of time and effort, but is very useful when planning the job, during the application, or even in the future, so we can tell if any new cracks have developed. Now, we will look at a typical resin injection project using a polyurethane 2-in-1 resin into a vertical crack. Firstly, we should open up the face of the crack with a grinding disc or a breaker, removing all loose material. The borehole positions are marked on either side of the crack. The narrower the crack, the closer together the packers need to be. Typically, this would be between 100 and 150 millimeters on alternate sides of the crack. Drill the boreholes, in this case 14 millimeter diameter, intersecting the crack about halfway through the wall thickness. Seal the face of the crack with a fast-setting mortar, or in the case of heavier water flows, a cementitious water stop. This helps to keep the resin within the crack matrix during the injection process. Next, insert the packers into the borehole and tighten. Each packer is injected in turn, working from the bottom upwards. If you're injecting with a 2-in-1 resin, then each packer is re-injected after 15 minutes. During the second injection, there is no water contact and the two-component polyurethane will cure to form an elastic solid body resin. It is normal to loosen or remove the next packer in the chain during injection. When you see the resin arriving at the open borehole, you will know that the section of the crack is fully filled. The packer is then replaced or retightened, and you continue injecting, moving along the crack until completely filled. After the second injection, allow the resin to fully cure. With most resins, this will take 24 hours. The packers can then be removed by unscrewing and the boreholes filled with the fast-setting water stop. If using one-day site packers, these can be removed immediately after the second injection. The boreholes are drilled at a 45-degree angle, as can be seen in the plan view, top right. These should intersect the crack or joint halfway through the depth of the structure. The boreholes continue a little beyond the crack. This helps to prevent drilling debris from clogging the pathway of the injection resin. The packers alternate from one side of the crack to the other. How do we know how much resin to inject? We can estimate consumption by looking at the theoretical volume of the main crack itself. It's unknown how much material will be lost at the back of the wall or into defects branching off it though. This is where the experience of the supplier or specialist contractor is so important. We will now look at a case study involving injection of a single component elastic foaming polyurethane. This is an 8 metre deep manhole on a new sewerage treatment works in Northumberland. Several attempts have been made by others at sealing the deep manhole, but they had all failed. The water ingress was quite extreme. Following a site visit and detailed investigation, a proposal was made and the client agreed to give this a go. If it failed, they were going to have to excavate the entire manhole and start again. In all complex injection jobs, the first thing to do is understand the structure. The original build of the manhole was fairly conventional. Firstly, a deep hole was excavated with a cast concrete base at the bottom. Precast manhole rings were then installed with a bituminous sealing strip between all the joints. We don't know why this structure originally failed, but it's possible that the sealing strip was missed from the lowest joint or it was improperly applied. To try and stop the water ingress, the contractor had installed a rigid plastic liner. This created an additional reservoir of water between the liner and the manhole ring, and it still leaked. They then installed an inner wall of concrete rings. This created yet another void for the water to flow into, and guess what happened? Yes, it still leaked. When the water was pumped out, there was a heavy flow of water entering at the wall-to-floor junction, creating a whirlpool effect. In this situation, the leaks had to be confined to a smaller area. This was done by using a water stop to gradually form a waterproof fillet around that bottom junction. Using this technique, the leakage was confined to 4 equally spaced outlet points. Boreholes were drilled and injection packers inserted into these points and again sealed around with a cementitious water stop. Hoses were connected to the packers and other ends of the hoses placed into a large bulk bin, together with a water pump. Now, all the leakage was coming through the 4 hoses into the bin before being pumped away. A situation had been achieved where no new leakage was spilling onto the floor of the manhole and the injection could be started. The injection was carried out with a fast-setting, elastic, single-component polyurethane. This has a reaction time of about 20 seconds. Each hose was injected in turn. During injection of the first position, a close eye was kept on the other 3 hoses. When resin entered through another hose, the first hose was then crimped and injection switched to the one the resin was coming out of. In this way, a continuity of injection was achieved all round the base. Once all the easiest pathways were sealed off, the expanding foam resin was pushed out through the original leak routes into the soil surrounding the base. After removal of the packers, the boreholes were filled with a mortar and everything left for a week to check for any further ingress. After a week, there were no leaks, so a new floor at the bottom of the manhole was cast with a high-strength, waterproof and chemically resistant sewer and shaft mortar. The second Severn crossing is a 5,128 metre long bridge between England and Wales. The centre position is a cable-stayed bridge with 2 approach viaducts. The bridge was completed in 1996 and is now the main entry point into Wales. The main carriageway is made up of 2,300 precast concrete sections. The picture on the right shows the inside of the bridge. The main roadway runs over the top. The lines you can see running across the top of the joints between the sections, they are bonded together, but more importantly, they are pulled together and kept under tension by steel cables running between concrete anchor blocks. During routine maintenance, a large number of small cracks were found in these blocks. After various tests, a full report was submitted to the Second Severn Crossing Authority. It was agreed that structural repair was necessary. It was further decided that a vacuum injection was the best way to proceed. Smoke testing had shown that the faults were interconnected, making a complex matrix of cracks in each block. In some areas, the cracks had created islands of concrete that were in danger of falling off if drilling or high-pressure injection was used. Here we have a visualization of the vacuum injection procedure. For each network of cracks, you need a vacuum point with an injection port and a header tube. For vacuum injection, stick-on packers or injection plates are used rather than drilling. For this project, the client used nylon blocks, which were drilled and tapped to take a threaded hose connection. The plates were fixed in place with a two-part adhesive. The same adhesive was then used to cover all visible cracks on the surface. The vacuum pump gently removes air and residual moisture from the crack network, creating a low-pressure area which is then ready to receive the injection resin. At this point, the inlet valve was opened and the resin released. A slight positive pressure was also applied on the injection side as this sped up the process. The resin flowed very easily into even the smallest of cracks and filled the header tube, which was fixed at an upright position. When the injection was finished, the vacuum side and the injection side were turned off. The fuller header tube was left open to provide a reservoir, replacing any material lost through slight leakage from the cracks. Once the resin had set, the header tube was then also removed. The main pieces of plant required are shown in this diagram. They are a vacuum pump, two pressure pots. They are airtight drums in which a vacuum or pressure is created, while separating the injection resin from the vacuum pump. On the inlet side, the resin is poured into the second pressure pot, and the pressure slowly increased to help push the resin out of that pressure pot. Here are some photos taken during the trials. You can see one of the pressure pots, and here a close-up of the injection plates. The injection was carried out at a very low pressure, so flexible hose was used with push-fit connections. Here is an area under injection. You can see some small amounts of resin running down, mainly from the intersection between the anchor block and the concrete wall. We can see that the resin has filled tiny cracks that were not even visible prior to the injection starting. The trial went extremely well, and a core sample was taken from the anchor block to confirm that the cracks were fully filled and that the adhesion to the concrete was good. Analysis of the core samples under electron microscope revealed that all cracks that could be found in the specimen were fully filled with resin. The smallest crack that they could find was 17 microns. That's 17 1,000th of a millimetre. This could be achieved with a very thin epoxy and by vacuum injection. The main contractor in the project has now changed, but the work is continuing using the same resin and procedure. We will now have a look in more detail at curtain injection. With curtain injection, we are aiming to install a complete coverage of the injected material across the earth retaining side of the structure. We install packers in a grid pattern across the surface. Curtain injection can be considered as an external waterproofing installed from the inside. A typical injection pattern is shown on the left-hand side. We call this 400mm centres. It is basically a 400 by 400mm square with an additional packer placed in the centre. The dimension D is the maximum distance between one packer and its nearest neighbour. Distance D works out at just over 280mm. The packers are injected in rotation, normally 3 times for each packer. After the first pass, the easiest pathways are sealed. During the second and third passes, the gel is forced into even the finest capillaries. The gel time is very important. With a longer gel time, you can get deeper penetration into finer pores. With a shorter gel time, you can seal heavier leakages very quickly. When you increase the temperature, you decrease the time it takes for the gel to react. Adding more salt has the same effect. The part B of the acrylic gels is a form of salt, so for the variable reaction gels, we can increase or decrease the amount of part B to speed up or slow down the reaction time. For a classic curtain injection, we completely drill through the wall and then use a gel packer which pushes the gel out sideways into the soil and at the back. The gel tends to form a dome shape. As we continue the injection process, the domes of gel overlap to form a continuous curtain of waterproof material at the back of the wall, eventually covering the entire area. An area injection is a slight variation on a curtain injection. We are sealing pathways within the wall rather than creating a barrier behind it. This technique would typically be used in thick masonry walls where there are a lot of voids between the bricks. In this situation, we don't drill all the way through the wall, but stop about 50mm from the back. The boreholes are normally drilled into the mortar joints, and we insert short packers at the wall face. By injecting the packers, we fill the boreholes and gel is forced out sideways into the defects. Therefore, the structure is infilled with the waterproof and elastic gel. As the wall is not sealed at the back, a certain amount of gel will inevitably leak out, sealing all the previous points of water ingress. If doing a full curtain injection on a brick wall, a combined injection is typically carried out. Drill the boreholes all the way through the wall, but insert small packers at the face of the wall. In this way, the gel is deposited at the back of the wall, curtain injection, but at the same time fill any voids within the wall with gel. One advantage is that small boreholes of down to 8mm, depending on the packer, as opposed to 18mm for the normal gel packers. This means curtain injection can normally be carried out without damaging brickwork. In 2016, there was a trial carried out by London Underground to test the effectiveness of a gel injection system for sealing brickwork tunnels. The trial area was located close to Farringdon Station on the Metropolitan line. The construction of the tunnel included multiple layers of brickwork with an assumed pitch-based waterproofing layer applied externally. Throughout this section of tunnel, there was evidence of water dripping through the brickwork with stalactites and heavy salt and soot contamination. The trial area had constant water leakage coming down through the brickwork at the tunnel's crown. This area had been highlighted on a London Underground report stating that the rails were at risk from corrosion due to ongoing leakage. In the images in front of you, you can see large steel deflector plates which had been mechanically fixed to the brickwork by London Underground. They are used as a temporary measure to divert water sideways, down the tunnel wall and onto the track bed. The brief was to provide an elastic, permanent repair with no detrimental effect to the structure or the trains passing through. Acrylic gel was used in combination with a cementitious-based water stop. A scaffold was erected to ensure a safe working platform. The work was scheduled over 2 consecutive night shifts. Each night, a lot of time was taken up with moving all the equipment from the platform to the trial location, setting up and then taking it back down again. There was about 2 hours each night to carry out the surface preparation and the injection works. Work started by removing one of the large metal sheets measuring 1 metre by 2 metres from the crest of the tunnel to allow access to the test area. A closer inspection of the surface revealed a thick crust of salt and soot contamination. This layer was removed mechanically as thoroughly as possible, whilst ensuring the brickwork was not disturbed. The worst leakage points were surface sealed using water stop before drilling boreholes and inserting 85mm packers. The injection ports were placed at 400mm centres in a grid pattern, with a single packer positioned in the centre as we detailed previously. 10mm boreholes were drilled to a predetermined depth so as not to penetrate the original pitch-based waterproofing assumed to be on the earth-retained side of the tunnel. The first 100mm of the boreholes was then re-drilled with a 14mm drill to widen out the hole to take a larger 14mm injection packer. The packer was inserted and tightened into place. The gel material was injected using a dedicated acrylic gel pump. These pumps deliver the part A and part B in a ratio of 1:1 to the mix head. In the picture, they are pumping a small amount of the mixed gel into an empty drum. By doing this, the contractor can check the mix rate at site temperature and humidity levels to see how long the gel would take to react. In this way, the time allowed between each pass of the injection packers could be correctly established. The packers were then re-injected one at a time in the grid pattern. Each packer was injected 3 times, but by the third pass, very little gel was entering the borehole and the dripping water had stopped. After 48 hours, the trial area had dried up completely, whereas the surrounding brickwork was still heavily leaking. Continuing with acrylic gels, we now turn our attention to expansion joints. To have a well-functioning expansion joint, you need a highly flexible and robust joint sealant. You also need to achieve a very good flank adhesion. This is a problem when repairing leaky joints. All expansion joint sealants require a good level of surface preparation. They should only be applied to a clean and dry surface. If you have a leaking expansion joint, then it's impossible to achieve this without first undertaking remedial measures. By pre-injecting with a polymer-modified acrylic gel, a very strong seal with a high flank adhesion can be achieved. Even in heavy leaking joints, the picture shows one application technique. In this situation, there is a centrally located water bar. Although the water bar is leaking, it is still used to help confine the injected gel to a specific area. Here, this is achieved by drilling a diagonal borehole, but it is also possible to use a needle injection through the water bar itself. In this cross-section, you can see the injection needles penetrating the centre water bar. This can be very labour-saving as it avoids the need to drill boreholes. These pictures are from a project where the technique was used. In the picture on the left, you are looking down into the joint after gel injection. In the centre of the joint is the water bar. The injection was through the water bar using needle injection. You can see the injected gel working its way around the water bar and showing at the side. This is clearly one of the points where the joint was leaking. On the right, we can see the same joint photographed with a thermal imaging camera. As the gel reacts, it becomes quite warm. So by using the thermal imaging, you can check the spread of the gel within the joint. There are many different types of joints. In the soffit joint shown, we have temporarily sealed the face of the joint with a fast-setting mortar. Then drilled a borehole and carried out the gel injection to seal the full depth of the joint. The temporary mortar is then ground out so that a new dry joint can be properly prepared and primed for the installation of a polysulfide joint sealant. This is an important point. Although the modified gel has amazing flank adhesion and elasticity, the one drawback for all gels is that they can dry out if they have no longer any water contact and are left open during warm conditions. Therefore, in most conditions, the gel is used within the joint, but with a different choice of sealant for the exposed surface. In this way, the gel is achieving a full elastic seal within the joint, and a traditional joint sealant is providing a hard-wearing surface treatment. Here we have a short video clip of the modified gel in action. You can see the outstanding elongation and flank adhesion, and a really good elastic recovery. The modified gel technique is increasingly used in new build as well as joint refurbishment. Imagine you have a situation where an expansion joint is to be covered, for instance under insulation or a floating screed, or in a podium deck under insulation and a floating screed, or in a podium deck that is going to be landscaped over. If you rely on a traditional joint sealant, then you know that at some point in the future that joint will fail. The cost of getting to that joint again to make a repair is massive. However, if you fill the main body of that joint with gel before sealing the top surface, you have a system that will last for the design life of the structure. You can also fill voids with acrylic gels. In this project for Network Rail, high voltage cable ducts were leaking. The client was worried about the insulation properties of a PU foam, possibly causing the cables to overheat. Therefore, a gel was chosen. The reaction time was designed so that the entire length of each duct could be injected within the gel time of that material. In other situations, gel can be poured directly into a cavity. Here we can see the setup with a pipe going from a hopper into a hole where a brick has been removed. The mixed gel is then poured in through a funnel. We can save on material and provide more stability by injecting or pouring the gel into a void that is already pre-filled with sand. The gel is so thin that it can easily fill the gaps between the grains of sand, providing a cost-effective and durable waterproofing within the void. For soil stabilisation, acrylic gels are ideal. They fill between the smallest soil particles and bind everything together, providing a waterproof and stable ground mass. The acrylic gels are environmentally friendly and have no adverse effect on groundwater or local watercourses. Soil stabilisation is a very complex subject, and a lot of research has been undertaken to check on the spread and curing times of the gel in different conditions. This is our test bed set up in Aurich, Germany. This can be filled with sand or any other combination of soils. The injection lances are inserted and the gel injected. After about 20 minutes, the side of the test bed is removed together with any loose sand. In this case, you can see that there are 3 distinct columns that have been formed by the gel and sand. These columns slightly overlap with each other, so this would be a perfect outcome if we are wanting to create a continuous vertical waterproofing barrier within the ground. The last injection system we are going to look at is microgrout. This is a cementitious material that is very finely ground and has a very good flow rate. Such materials have a high final compressive strength and are shrinkage compensated. We started looking at microgrouts for cracks over 2 millimeters in width and for void filling where a high strength is required. This picture is typical of a project where microgrout can be used. You can see voids at the surface of the concrete with the rebar cage exposed. Either the rebar has been packed too tight or the concrete hasn't been well vibrated. Here we will need to fill the void with something that looks like concrete, has the strength of concrete, and is also waterproof. Microgrouts are ideal. Microgrouts are usually injected through impact or lamellopackers. Using a driving tool, as shown on the left, the packers are typically larger than for resin injection. For an 18mm borehole and normally come without a ball valve. The type of packer shown in the picture has a yellow cap that can be clipped on after injection to prevent the grout running back out. The material is injected using a grout pump or a peristaltic pump. In some cases where the void is open at the top, it can also be poured. The picture to the right is the underside of a concrete deck after the shutters were struck. There were very large voids within the concrete. The rebar was packed very tight, and it seems like the aggregate in the concrete just never made it through to the bottom. To tackle this, the underside of the slab was shuttered off and sealed around the edge. From the top, 18mm boreholes were drilled, lamellopackers inserted. A number of vent holes were also required, so when the microgrout was injected, the air within the void could easily escape. When the injection was finished, the microgrout could be seen flowing out of the vent holes, proving that the whole void was filled. After 24 hours, shutters were removed, the packers snapped off, and the boreholes filled flush using a fast-setting mortar. The image shows the repair immediately after the shutter was removed. The microgrout looks darker than the surrounding concrete, but as it cures, it becomes lighter. This type of large structural repair can really only be done using a microgrout. With a troweled repair mortar, it would be impossible to fill all the gaps around the rebar. An epoxy resin used in this volume would generate too much heat, causing it to then shrink back as it cooled. So, did anyone think of a good answer to the question I posed at the beginning? Well, cracks can be caused by many different factors. Generally, I like to think of a crack as an unplanned movement joint. The structure at that point is wanting to pull in many different directions, but there is no movement joint, so it makes its own. That's why generally we use elastic materials for crack sealing, except in cases where a structural repair is required. If we are making a structural repair, then we should ask the question, has the building finished moving? If the building is still wanting to move, then as well as a crack repair, we may also consider some alterations to the structure with the help of a structural engineer. That brings us to the end of our CPD, injectable systems for cracks, joints, voids and curtain waterproofing. There are many different things we can do with injection systems: leak stopping, structural crack repairs, soil stabilisation, expansion joint refurbishment and void filling. With all the different products and techniques that can be used, it's really just a case of matching the right product with the right technique for the right project. At Coster, we have a virtual toolbox of injectable materials. By that I mean we look at each project, we have many different systems, application techniques and product combinations to choose from. If the only tool in your toolbox is a hammer, then every problem just looks like a nail. If you have many different tools available, then you can solve the problem in the most suitable way and achieve a permanent solution. Thank you for completing our CPD. To obtain your official CPD certificate, please contact me at technical@costeruk.com. Include in the email your name, the name of your practice, the title of the CPD, and the date of completion. And answer the following 3 questions. So question 1, what are the 4 types of injectable materials? Question 2, what materials would you use against a heavy water ingress? And question 3, what is a crack? Thank you very much for your participation, and I look forward to hearing from you.